Let's do another standard example where we have to use theorem 5.19. The integral that we're asked to find is 1 over x times square root of 4x squared minus 9 dx. So let me write down the relevant part of theorem 5.19. It states that the antiderivative of 1 over u square root of u squared minus a squared du is equal to 1 over a arc secant of the absolute value of u over a plus a constant of integration. So we see this one applies because we have variable squared minus constant squared. So let's determine what the values of u and a are. So we have minus the constant squared, so we see that a squared equals 9, and we see that u squared equals 4x squared. And from that, it follows that it follows that a is 3 and that u equals 2x. And with that substitution, we can then write du dx equals 2, du equals 2 dx, or 1/2 du equals dx. And when we use that substitution in our original integral, that integral becomes 1 over, and then we have x, and then square root of, this becomes u squared. So you can replace that by u squared. And then minus a squared, so that's our 3 squared. Now, and then we have to replace our dx with 1/2 du before I go further. Now, we have a small problem here, because after our substitution, we're still left with an x, and so I can't continue and just ignore that x. But fortunately, since our substitution is so straightforward, u equals 2x, it's easy to solve that for x. And we can do that on the side here, and we can see that 1/2 u equals x. So we want to replace this x here with 1/2 u. And then one thing that you see then is that this 1/2 shows up in the denominator. This 1/2 would go in the numerator. So this 1/2 and this 1/2 cancel out. And so that means we can simplify our integral as follows. It's 1 over u square root of u squared minus 3 squared du. So just to make this a little bit clearer, this u is what is left over from replacing the x with 1/2 u. And the 1/2's canceled out. And so now compare that with theorem 5.19.3. We see that the answer is 1 over a, and a is 3. So we have 3 here, and then secant of the absolute value of u, and then u, and then in the denominator we have a there, and that's 3, and then plus c. And then our final answer here is 1 over 3 arcsecant of, and all we need to do is replace that u by the substitution we made, and u was 2x. So we have the absolute value of 2x, and then divide that by 3, add our constant of integration. And that is our final answer. Now, if our integral is not in the standard form, we may have to use the completing the square. So this helps when quadratic functions are involved. And I'll give you a quick refresher on how to do that here. So we look at a general quadratic term, which looks like x squared plus bx plus c. And we can assume that the leading coefficient is 1. If not, you just divide by everything and just factor that out. So if there was a 2x squared, we could factor that 2 out of the entire expression and then put that 2 back in the end. So if we have x squared plus bx plus c as the general quadratic expression, then what we're going to do is we're going to add b over 2 squared and then subtract it. So if you do that, the net result is basically saying this is plus 0. Now, the reason why you want to add b over 2 squared in the first place is because you want to create a perfect square. So you see that the first part of this expression is a perfect square. Namely, we can write this as x plus b over 2, and then that whole quantity squared. So x plus b over 2 squared. And then what we need to do is we need to subtract that b over 2 squared that we added, and then we just keep the plus c. So this is completing the square for x squared plus bx plus c. And to give you kind of a way how this works in practice is you want to look at what is the term in front of the x. That's plus b. So, and then you take that plus b and you divide it by 2. So you take half of that, and now that ends up inside the parentheses with the x, and you square that. And then that b over 2, whatever is inside, you square and subtract that. And then you just keep the plus c that's at the end. So let's see how this can be useful in the following example. So we want to find the antiderivative of 1 over x squared minus 4x plus 7 dx. What we need to do is we need to rewrite this quadratic expression here. So let's do that. We have our x squared minus 4x plus 7. And I'm going to take a look at what's in front of the x, that's negative 4. And I'm going to take half of that. I'm going to tuck that into the parentheses here. So I'm going to have x, And then half of negative 4 gives me negative 2. And then I take that negative 2, I square and subtract it. So I can take my 2, square it, and subtract. So I take half, and then square, and subtract. And then I should not forget about the plus 7 in the end. So I have plus 7 there. And after completing the square, I end up with x minus 2 squared minus 4 plus 7 gives me plus 3. Okay, so let's use that to rewrite our integral 1 over x squared minus 4x plus 7 dx becomes 1 over x minus 2 squared plus, and I'm going to write that as a square as well by writing square root of 3 squared dx. So now hopefully you'll recognize this as something of the form u squared plus a squared 1 over, and that's part of theorem 5.19. So the substitution that we want to use here is that u equals x minus 2. And fortunately, du equals dx, so this is going to be a very simple substitution. And then we also have that a equals square root of 3. So this, the antiderivative of this integral is going to be, and let me maybe repeat the relevant part of theorem 5.19. Says that 1 over u squared plus a squared du equals 1 over a times arctangent of u over a plus a constant of integration. So with a being square root of 3, this integral becomes 1 over square root of 3 times the arctangent of u, and u was x minus 2. So we have x minus 2, and then we divide that by square root of 3, and then plus c. So that is our final answer. Again, do not worry about getting that square root out of the denominator. If you leave your final answer like that, it will get full credit.